So we show how we determine the rate law by using experimental information. We talked about two ways to do rates. One way is we can find the change in A over the change in time, and that will give us rates. That was the first method that we used. The second one is we determine the rate law where we have the rate constant and the concentration. So both of these will give you rates. One has time in it, one has concentration. So now we're going to show you how concentration and time relate to one another. So what we're going to do is we're going to set them equal to each other. And again, for this type of integrated rate law, we're only looking at very specific types of chemical reactions. And so these chemical reactions are reactions that only encounter one reactant in the equation. So for these integrated rate laws, we're always looking at the reactants, and it's always an equation that has one reactant in it. If it had two reactants, it's going to change the integrated rate laws. So for this, we're only looking at one reactant systems. And so what we do is we set both of these rate equations equal to each other, and we get something that looks like this. So we move the time to one side and the A's, the concentrations, to the other side, and we get this equation right here. And this is actually a differential equation that you can solve using Diffie differential equations. And when you use differential equations, you get this as the solution to this differential equation. And so this is a first order reaction. So for a first order reaction, if you take the ln of the initial concentration over the concentration at time t, it's going to equal a constant times time. The constant is the rate constant, and time, of course, is the time it takes for that concentration to decrease to that particular for that particular time to get to the final concentration. So again, what we did to go from this equation in the maroon circle to get the ln, we did differential equations to solve for it. Now you don't have to worry about that. We're not going to be solving them using differential equations, but that's how they jump from here to here. They use differential equations. So for a first order reaction, this is what we call the integrated rate law. And so we'll see on the next slide, you can rearrange this to get it into a linear equation form, and you can plot to determine whether or not something is first order just by graphing two variables. Now for second order, we do the same thing. We get this equation here. So we put the two rate equations together. And then when we do differential equations, we get this for the second order integrated rate law. So again, this shows you how concentration and time are related to one another. So we look at what's called the integrated rate law. And then lastly, we have the zero order. So for the zero order, we have this expression. And so when you do differential equations, you get this for the zero order integrated rate law. Now, there are a third order and so forth integrated rate law, but we're only going to look at these three for this course. So if you go onto Google, you can find out the third order integrated rate law, the fourth order, the nth order integrated rate law. But we're only going to stick to these three integrated rate laws. You don't have to memorize the equation, but you got to know which equation goes with which order of reaction and how to utilize the equation. So like I said, we can plot data, and if you plot data, you can determine whether something is a first order, second order, or zero order. So we look at the integrated rate laws. If you plot ln of A versus T, you should get a linear relationship, and the slope is equal to negative K. So that tells us the rate constant for this reaction. So again, we take the ln of A on the y-axis, time on the x. If we get a linear relationship, that tells us that this reaction is first order, and the slope equals the rate constant. Now, if you did the first order and it wasn't, and you try a second order, what we plot here is 1 over a versus time. And when you plot 1 over a versus time, again, you get a linear fit or linear curve, and the slope equals the rate constant. And then lastly, if you plot concentration versus time, you should get a linear relationship if it's zero order, and again, it'll be a negative slope because over time concentration decreases, and so slope equals negative k. So again, by plotting the data, you can determine whether something is first, second, or zero order. You just get your concentration, you get your time. If you want to know first order, you plot ln of concentration versus time. Second order is 1 over concentration versus time. And zero order is just concentration versus time. So if any one of these forms a linear plot, that tells you that's the order of reaction. Now for first order in particular, we're going to go a little bit more in depth about first order reactions and talk about what's referred to as the half-life. And so the half-life, maybe you've heard about it when you're talking about radioactive material or carbon-14 dating. What happens is over time, over a certain period of time, the original concentration loses half of its concentration. So for carbon-14, starting at time 0, after a certain number of years, it loses half its concentration, and another certain number of years, it loses another half, and it keeps on going. It splits in half and half as time progresses. And so this is for a, actually for first order, we use it quite a bit, but this is also for second and zero order as well. So you can calculate the half-life of a reaction by knowing if it's first, second, or zero. If it's first order, it's simply just taking the ln of 2 divided by k. So the first order reaction's half-life is not dependent on concentration. So again, the first order half-life is independent of concentration. So it doesn't matter the amount of your initial concentration, it just matters on the rate constant. And for I would say most radioactive decay processes, they're first order reactions. So this is how you can calculate the half-life of radioactive decays by knowing the rate constant, and ln of 2 divided by that will give you the half-life. So again, first order half-lives are independent of initial concentration. For second order, it is dependent on the initial concentration. And by the way, you can take the integrated rate laws we saw on the first slide and calculate these equations. You just set AT as 50%, and then you can calculate the half-life equations I'm showing you here. So second order process is dependent on initial concentration. Same goes for zero order process. It is also dependent on initial concentration as well. And so we use half-lives to kind of gauge, how long it would take for a substance to, for example, to go through 3 half-lives. So you just take the half-life, multiply by 3, that'll tell you how long it takes for a substance or a reactant to decay by 3 half-lives if it's radioactive decay. And so this is where it's very important to understand the units for the rate constant, because in a lot of these problems, it won't tell you whether something is zero order, first order, or second order. they'll just tell you that the rate constant is this, and it'll give you the units of the rate constant. And so from the units of the rate constant, you can determine what order of reaction it is. And if you want to refresh on that, if you go to the lecture we did on Wednesday, we talked about the different units for the different orders of reaction. But in this question here, we have the thermal decomposition of phosphine into phosphorus and molecular hydrogen is a first order reaction. So note here we only have one reactant. It gives us the half-life of the reaction is 35 at 680 degrees Celsius. Calculate the time required for 95% of the phosphine to decompose. And since I didn't put the unit down, we'll just write the unit of time is second. So it takes 35 seconds for the half-life. So before we begin anything, I just want to show you kind of qualitatively how we can kind of estimate the time it's going to take. So notice we want to know how long it takes 95% of the phosphine to decompose. So if we look at our half-lives, if we start with the first half-life, we start with 100%, we go to 50%. This took 35 seconds. Now from 50%, if we do another half-life, we get 25% is left. This took another 35 seconds. We do another half-life, so all we're doing is we're decreasing the concentration by half each time. We get 12.5%. This took another 35 seconds. We do it again. We get 6.25% of the original sample remains. Again, this took another 35 seconds. And if we do it again, I think this is 3.125, but let me double check. Yeah, we get 3.125%. And so the reason I'm showing you this is because from this, you can kind of deduce where the time it will take for it to be 95% decomposed. Because if it's 95% decomposed, that tells us that there's only 5% left. And 5% left would fall between 1, 2, 3, 4, 4 half-lives and 5 half-lives would be 5% here. So if we looked at the time for 4 half-lives, it would be 140 seconds, and 5 half-lives, 175 seconds. So we should be able to say for it to be 95% decomposed, it's going to occur between this number range, because that's between 4 and 5 half-lives. So 5% falls between those two numbers. So this is just kind of give you an idea of the amount of time it's going to take. Now we're actually going to calculate the amount of time. This is more of a qualitative assessment. And so, for example, if this was a multiple choice question and there were a series of different times given, just like a question like this, well, you can say, hey, it's going to be between 140 and 175. So you look at all the different answer choices. If only one of them is between 140 and 175, that's a good indication that that's the correct answer. So make sure you don't have to do any of the calculation. You can just select it. So now let's look at the problem. So this is a first order reaction. So we're going to use ln of AT equals negative KT plus ln of A naught. So this is the first order integrated rate law. So we don't have the initial concentration, but we know that at the initial time we have 100%. And we know that at time t, we have 5%. So we know the concentrations, or at least the percent of concentration. What we don't know is K. And so for K, we have to use the half-life to determine K. So if we think about what we saw on the last slide, T1 half equals 0.693 divided by K. So if we know the half-life, we can find K. So K equals 0.693 divided by 35. And we get K to be 0.0. Oops. 0.0198. So now we have K. We can set it up. So what I'm going to do for the initial concentration is, instead of using a percent, I'm just going to use 1. So the initial concentration is 1. The final concentration is 0.05. And you can only do this for a first order reaction. You can use the percents and put those into numbers just like this and solve the problem. This doesn't work for other than first order integrated rate laws. If you go to second order or third order, you actually have to find the percent of the actual concentration of for the percent. 5%, you would take 5% of the initial concentration. So now we set this up, we get ln of 0.05 equals negative. And the beauty about this is that ln of 1 is 0. So this goes to 0. So therefore we just have ln of 0.05 equals negative 0.0198 K. So now if we take the ln of 0.05, we get negative 2.996. Oh, it's T. Sorry, we're looking for T here. So now we can solve for T. And again, for T, time, it's always going to be positive, so your negative signs should cancel out. If they don't, that's an indication that you've done something wrong. And we get 151 seconds. So just like we predicted, it would fall within a certain range. It did. It fell within the 140 to 175 range. So here we have the decomposition of cyclobutane at 500 degrees Celsius is 0.0092 second inverse. How long will it take 80% of the sample of a 0.1 molar solution of cyclobutane to decompose? So here it doesn't give us the order of reaction, but it gives us the equation. But if it didn't give us the equation, from the rate constant, we can determine the order of reactions. So since the rate constant is in second inverse, this means it's a first order reaction. So now we want to see how long it will take 80% of the sample to decompose. Now, if you want, you can take 80% of 0.1, but since this is a first order reaction, all we need to do is we can say A naught equals 1, and if it takes 80% of the sample to decompose, it means only 20% remains. So AT equals 0.2. Again, you can do this because it's the ln. It has ln in the equations. And so the K is 0.0092. So now we can set this up and solve for T. And again, the ln of 1 is 0. So that we can just drop off, and we get negative 1.6094 equals negative 0.0092t. So now we can solve for t and determine how long it will take for 80% of it to decompose. And it'll be 175 seconds. So that's how long it would take for 80% of the sample to decompose. So I'll do one more example, and then we'll take a brief pause. So here we have a certain reaction where A goes to products, has a rate constant of 0.122, molarity inverse, minute inverse, starting with an A naught of 1.01. How many seconds will it take A to reach a concentration of 0.750? So in this problem, it gives us the rate constant. It gives us the concentration at A naught and the concentration at AT, and asks how many seconds will it take. Now if we look at the rate constant is in molarity inverse minute inverse. So if it's in molarity inverse minute inverse, this means it's a second order reaction. And notice that the time unit is in minutes. So when we solve for time here, it's going to put it in minutes, and then we need to convert to seconds. And so the integrated rate law for second order is 1 over AT equals KT plus 1 over A naught. So we know our initial concentration, we know our concentration at time t, we know our rate constant, we can determine the time it will take to reach this concentration. So let me set it up. So 1 over 0.75 equals simplify, we get now we can solve for t. And we get 2.81, and this is minutes. So then to get it to seconds, we got to multiply by 60. We get 169 seconds. So that's how long it will take to decrease the concentration from 1.01 to 0.75. Notice here, though, that one way you can kind of know that this is not going to be a first order reaction is that it gives you actual concentrations. So if it gives you actual concentrations, you know, there could be a marker that says, hey, this may not be first order reaction, because you don't technically need the concentrations to do a first order integrated rate law. You could use, if they give you percents, you can just use the percents to do it. But for zero order and second order, you need at least the initial concentration of the sample. So here we have another example involving nuclear stress tests using gamma-emitted radioisotopes, thallium-201. Follows the flow of blood through the heart at rest and under stress. The half-life for this decay of thallium-201 is 72.9 hours. Calculate how long it would take for the amount of thallium-201 to fall to 5% of its original value. So, as I said before, with most radioactive decays, these are first order reactions. The way you can confirm this is if you look at the half-life unit is only time. So anytime you see that the half-life unit only has the unit of time in it, it's a first order reaction. So here thallium-201 is half-life of 72.9 hours. Calculate how long it would take to fall to 5% of its original value. And so I'll show you kind of a qualitative way to do this. If we start at 100%, we go to 50%, 25%, 12.5%, 6.25%, and then we have 3.125%. And so each half-life is 72.9 hours. So we can kind of estimate how long it's going to take because it's between 4 and 5 half-lives. So we can say it's 4 times 72.9, 292, 5 times, and 365 hours. So when we calculate how long it's going to take, it's going to fall somewhere between this time range. So now in order to solve for the time, we need the integrated rate law for a first order reaction. So the AT and A naught we can set to, we'll set to 1, representing the initial amount. So a whole complete amount, like 100%, we put 1. And for AT, 5% of that would be 0.05. Now we need K in order to solve for time. So the way we find K is through the half-life. So for a first order reaction, T1 half equals 0.693 divided by K. So K equals 0.693 divided by T1 half. So if we know the half-life, we can find K. And this K is going to be in hours inverse because our time is in hours. So K equals 0.693 divided by 72.9. And we get 9.51 e to the -3. So that's K. Now we have K, we can find the time. So ln of 0.05 equals negative. And again, the ln of 1 is 0. Yeah, it's supposed to be t to the 1/2. All right, not t to the 12. There you go. It's the half-life. So ln of 1 is 0. So then we just have this to left to simplify to solve for t. And so if we did it correctly, the negative sign should cancel and we can determine t. And again, time would be in hours. And we get 315 hours. So note that the time we calculated is in between the range that we predicted, the half-life, or we predicted based on the half-lives. So it'll take 315 hours to get to 5% of its original value. So again, with integrated rate laws, the most important thing is to pick the right equation to solve for whatever you're looking for, whether it be time or concentration. And the way you usually determine the order of reaction is by looking at the rate constant. So knowing the units of the rate constant is important in order to know what order of reaction it is.